fancy, huh?
Oh, that looks not real. It's a .gif.
But why is there 2 mouses on the screen?
Oh, wait.
Because it's magic, Victoria. Because it's magic.
When did you get
No, but did you see them? So 2
What's that?
arrows.
Yes.
Why is it there?
Because I control one of these channels.
No, but that's
Dual wielding lightsaber.
Okay, no.
All right. Heat energy. This is a fire. It releases heat. Very fancy.
That's
Even more fancier.
All right. So we're going to talk. This unit is specifically about heat energy, but we'll start off with just some general information about energy in general. So as we've talked about before, and that this is why you should be familiar with the law of conservation of matter and energy, because we talked a little bit about this. Anything in the universe can be classified as either matter or energy, one of the two. Matter is anything that has mass and volume. That's the definition of matter. It has mass and takes up space.
That's good.
Or, if it's not matter, then it must be energy. And we have 2 types of energy that we talk about, 2 general types. Kinetic energy, which is energy of motion, energy of moving molecules.
Where do they get connects from?
What's that?
Where do they get connects from?
Yeah, because you're moving the use of the connect.
That's cool.
So for example, water flowing down a stream is an example of kinetic energy. It's moving water that contains energy. Versus potential energy, which is stored energy. Sometimes it's called energy of position. It's energy that could be used later. So kinetic energy can do work, and we'll talk more about this in our physics unit. But kinetic energy can do work. Potential energy could be used to create kinetic energy to do work. For example, water stored up behind a dam has a great deal of potential energy. How is it used? Andrew?
They have like these little sections in the dam where the water flows through and like spins a turbine to generate energy.
Yeah, they let some of this water through. And when they do so, what is that potential energy being turned into? Kinetic energy. It's the stored energy. This kinetic is transformed into kinetic energy, which is moving energy, which can then turn a turbine, which can generate electricity, and so on. So kinetic energy and potential energy can be transformed from one to the other.
What about wind?
Wind energy is the moving molecules of wind are a form of kinetic energy. A battery contains potential energy, has the potential for electrons from one electrode to move to the other, and that's, again, potential energy. Once you attach some sort of device to it, then you transform those electrons, move, and then you're creating kinetic energy. So like I said, the law of conservation of matter says that matter and energy cannot be created, cannot be destroyed, but they can only be transformed. So solar energy, for example, in your calculator is transformed into what type of energy? What kind? Solar energy. What does your calculator do with that solar energy? It uses it in what form?
It stores it for later use.
But what's happening? The sun is not like powering the display. It's transformed from solar energy into close electrical energy. The energy of electrons.
Wow.
And that's what powers your calculator. So as some examples, you have Mr. Akiri here shooting his bow and arrow. Okay. As you pull the bow back, okay, that has potential energy. Energy of position, stored up energy, and if he lets go, it's transformed into kinetic energy. Or again, this weight suspended up above the surface has potential energy. That energy can be transformed by cutting that rope and that weight would fall, being transformed into kinetic energy. Okay, Mr. Arcuri playing with his little paddle and ball.
Must have been young.
Okay. Back. All right, so we're going to talk about heat. In this unit, we're talking about energy, and we're talking about heat energy. So heat energy, what makes something hot? So if you have two metal rods, one's burning hot and one is not, what's the difference between the two? Kayla?
The burning hot one has a lot of molecules burning together really fast.
Yeah, it's the movement of the molecules. Heat energy is created by vibrating molecules. And the faster the molecules vibrate, the warmer the object, the more heat energy it gets.
Doesn't all vibration result in sound?
In sound? No.
No.
In heat, but not sound.
So, if for like an instrument, if you were playing it, that vibration is what makes it sound.
Yes.
So it's technically heating up too.
No, because you're vibrating a large sort of surface. It's not so much, you're not, I mean, I'm sure there's some change in heat as you put your bow across the strings due to friction. But overall, it's that whole string that's vibrating that's creating the sound. And as materials are heated, generally, as the temperature increases, the molecules vibrate faster, and they also spread farther apart. That is called thermal expansion. That usually, when you heat up a substance, it expands, gets larger. Okay? The molecules move faster, they spread out, becoming larger. So if we look at a couple solids, for example, one that's colder than the other, you see greater vibrations in the hot one, and an expansion in the volume of the material. So just about all matter expands when its temperature is increased and contracts when its temperature is decreased.
That would not apply to ice and stuff.
There's one important exception, which is what? What did you say, Yusuf? Water. Water is an exception. Because if you take water, that's 33 degrees. So, and then you let's say if you have water that's 33 degrees in a lake, and then you decrease the temperature to 32 degrees, what would happen to the water? First, what happens? It freezes. Okay? If it also contracted, what would happen to the ice? Well, if it contracts, what happens to its density?
Always decreases.
Its density would increase. What would happen in the liquid water? If something's more dense in a liquid, what happens to it? It sinks. Is that what happens to ice in a lake? No, it doesn't. If that did happen, lakes would freeze from the bottom up. They would freeze solid. And could anything live there? Not much. But they don't. Water is an exception. When you take water from 33 degrees, for example, to 32 degrees, it does become a solid. But when it becomes a solid, it actually expands. Because of the crystalline nature of the water molecule, it expands, becoming less dense, and therefore it floats on top of the water. So water is one of the exceptions. Okay? So a thermometer works based on this principle of thermal expansion. Okay? Inside of a thermometer, you know, a traditional thermometer, not an electronic one, there's either, most thermometers today have alcohol in them. Like if they're red or blue, it's probably alcohol. Older thermometers used to have mercury in them, which was more accurate, I think. But why is it not used anymore? Poisonous. It's a heavy metal that's poisonous and should not be out in the environment. You should not ingest it or inhale it. So it's generally not used very often anymore, mercury. But it works on the principle of thermal expansion because in the bulb of a thermometer, oh, there's a thermometer up there. So in this thermometer, it's pretty clear. Down at the bottom in that blue section, that's the bulb of the thermometer. There's some alcohol. As this roux warms up and that alcohol warms up, what does it do? It expands and it rises up higher in the central tube. It's calibrated so that people have marked on that tube what temperature is indicated. And as it cools down, that contracts and it moves lower down. Did you ever see one of those, I think they're called Galileo thermometers? It's like a cylinder of a liquid with little weights of different colors hanging in it.
No,
Ever seen those?
I have. I've seen one where you hold it in your hand.
And they, what those things do is, because as the temperature of that liquid changes, its density changes, and those weights either sink or float depending on the temperature, and you use that to tell the temperature of the room. It's the same basic idea. So as this liquid warms up, it expands, goes up the tube, and it's marked to show the correct temperature.
What about if you like put a just can of water in the freezer?
Can of water in the freezer.
Oh, wouldn't it just like expand?
Yeah, if you ever accidentally put like something, a water bottle in the freezer, if you fill it all the way and put it in, it's going to break. Because as the ice expands, it breaks.
So it says it contracts when the temperature decreases.
Because waters, remember that exception. That when water freezes, it expands. But it's an exception because most things, as you decrease the temperature, contract. So that's why it's different. Victoria?
What makes like you know how you said like mercury like is more accurate than alcohol? What makes it like more accurate?
It has greater, I think because it has greater changes for the temperature. Because it's a metal, I believe that's why it's more accurate, that it shows a greater difference. And here's some examples of things that are, we have to think about thermal expansion around our area because we go through extremes in our weather. In the summer it can be 95 degrees, in the winter it could be 0 degrees. If you ever notice, like in the sidewalk, right? I used to pour sidewalks sometimes when I was working construction, and every couple sections of the sidewalk, do you ever notice what's in between? Like some are just, there's just like a little indentation, but in some they put a piece of plastic, a piece of rubber, a piece of felt in between the two sections of sidewalk. And that's because of thermal expansion, so that when it gets hot in the sidewalk, the concrete expands. That is there, because if it wasn't there, if it was just concrete to concrete, and they expand, they would buckle. In my house, I put in a floor, a new floor, a laminate floor that sits on top, but all around the edge, you have to leave a gap of like 1/4 of an inch all around. Again, for the same reasons, thermal expansion. That in the summertime, when that wood in there expands, if you were tight up against the wall, it would buckle and pop up. If you bought hardwood floors in your house, you have to keep, if you're putting new hardwoods in, you have to keep them in the room you're going to install them for several days to allow them to acclimate to that temperature before you actually install them to be sure they don't expand. In the summertime, your doors sometimes stick in your house maybe because of thermal expansion of that and because of the moisture. So there's all sorts of ways. This is showing a grate in a bridge. So like bridges, for example, when you go over the joint between where the road and the bridge, they have these expansion joints where if it's in the hot weather, okay, those expansion joints as the road expands, they would go and be pushed in closer together. In the winter, as it contracts, they pull out, but they don't pull out so much that there's a gap there. So those are to allow for expansion so that things don't buckle. When people say if you can't get the lid off the jar, you should put it under hot water. Again, the reason for that is because the metal in the lid can expand, loosening it up a little bit. And loosening and loosening, the same thing, don't forget.
I don't think that. But I'm listening to
It could be dangerous.
There's another thing that happens once in a while is in cold regions, sometimes railroad tracks, which are just basically a long metal track, sometimes they, because of the cold, they contract so much that a gap can form between the rail. And so sometimes what they do is it's called burning the rope, whereas a crew will go on if there's a gap in the track and they need to repair it. They'll take a big long rope, nylon rope, they'll soak it in kerosene, they'll lay it along the track and then light it on fire. And basically that's what they're doing right here. And as that warms up the rail, It expands and then it eventually reconnects and then they can make their repair. So it's based on this idea of thermal expansion.
Sounds like fun.
Yeah, we can do that.
Smells like
Okay, so what temperature scale? So if you look out, you use your Weather Channel app or something, or you went online and looked at the temperature. You heard it on the news. What units are they generally using here? Yeah, Fahrenheit. Okay. There are a variety of temperature scales that can be used. We are probably most familiar with Fahrenheit if you grew up in the United States. Most other countries do not use Fahrenheit. What do they use? Celsius. Celsius is the metric measurement of temperature. But again, we don't generally use Fahrenheit. Celsius. So here's an idea. These are three temperatures. There's also one called Kelvin. Okay. And does anyone know what Kelvin is used for? Yeah.
Well, it's more of a scientific one.
Yeah, it's used like in research, generally at very low temperatures. Okay. So anyway, what you see here on this scale, it shows you sort of the equivalence. So 32 degrees Fahrenheit is 0 degrees Celsius, is 273 degrees Kelvin. Okay. 212 degrees Fahrenheit is 100 degrees Celsius, which is 373 degrees Kelvin.
For Kelvin, isn't 0 like absolute 0? You can't get lower than that?
Yeah, and the Kelvin scale, 0 degrees Kelvin is what's called absolute 0. So as you cool something down, what happens to the vibration of the molecules? They slow down, right? The colder it is, the slower the molecules vibrate. So logically then, if you continue to cool down a substance, what will eventually happen?
Stop.
That the molecules stop moving altogether. That temperature is called absolute 0, when the movement of molecules stops. Now, thus far, scientists have never been able to achieve absolute 0. They've gotten into very, very close fractions of a degree within absolute 0, but not down to absolute 0.
On the news, I heard that they were wrong about absolute zeros, that it can be even lower.
Even lower than 0 degrees Kelvin? Interesting. Matthew?
if like when something gets extremely cold, it turns into a solid. Then how come liquid nitrogen stays like a liquid? It's like
It just has a much lower freezing point. So it still would reach a solid state, but it's at a much, much lower temperature. Victoria?
How do they test how do they know like when they get to absolute zero? Like,
Just by extrapolating back from, you know that the molecules slow down this amount when you lower their temperature 10 degrees. So if you sort of work your way back, then eventually you can trace back to the temperature when they stop altogether. But that's sort of paradoxical. This is not really related. But if I'm going to walk across the room, if I say, here's my rule, starting here, each time I'm going to walk halfway across the room. Right? So if I start off and I walk halfway across the room, all right. Now I'm going to do the same thing. I walk halfway across the room from here to the other. When will I reach the end of the room? Jack?
Never.
Never. I'll never reach the end of the room.
I don't get it.
Because now I got to walk halfway again, right? All right? Now what? Halfway. 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 There's always going to be some gap because I'm never going the full way there. That space will get smaller and smaller, but am I ever going to actually reach the wall? No.
If you go
Yeah.
if you keep going halfway, won't you eventually reach the end of the
No, because you're always taking half of what's left. Half of what's
If
left.
there was something left,
There's always something left, so you're always only going halfway. You're never going to quite get there. Yes, sir? Could they make what colder? No, I mean, because it's almost impossible to lower the temperature if it is that low. Because that's negative 273 degrees Celsius. So if you think like liquid nitrogen is very cold, that's nothing compared to absolute zero. There's some temperatures that you guys are going to need to memorize. And I think most of them you already know. One is human body temperature. Now this varies, and different people have slightly different average body temperatures. But what we say for our usual average body temperature is what? 98.6 what? Degrees Fahrenheit. What about Celsius? What's body temperature in Celsius? Right?
37 degrees.
37 degrees Celsius. Okay. So you should remember both of those. 98.6 degrees Fahrenheit, 37 degrees Celsius is body temperature. Room temperature. Now, obviously the temperature of a room fluctuates, especially in this room. But what we generally say for room temperature, you know what you said?
86.
No, it'd be pretty warm for room temperature. If you're in a room that's 86, you're pretty hot. A little higher than that. Kayla?
65.
A little bit higher. We say generally 68 is the number we're going to use. And that's 20 degrees Celsius.
It was close.
Question, Victoria?
No, what is it?
Victoria, freezing point of water in Fahrenheit?
32 degrees.
32 degrees Fahrenheit. And Celsius? 0 degrees. The boiling point of water in Fahrenheit, Nicholas? 212 degrees Fahrenheit. And Vedant, how about Celsius?
100 degrees.
100 degrees.
Also, you know the boiling point of water is where you are.
Yeah, it will vary depending on altitude. Also, it varies depending on any dissolved substances. Is the other big factor. Victoria?
You see how there's like all those numbers and then there's like that on the thermometer?
Yes?
What is that? It says like 5 degrees, 9 degrees.
Oh, that's just showing like that amount of space. In Kelvin and Celsius is both 5 degrees, but in the Fahrenheit scale that difference would be 9 degrees.
How did your half thing?
What's that?
How did your half of the room thing apply?
Oh, because I don't know, I was sort of going based on extrapolating
I
back.
still-
If
I
you
still don't
decrease the temperature 10 degrees, I don't know, I guess it
But
doesn't
isn't
really.
it like just got like just a minute left? Like,
Yeah, and you always go half to
Yeah.
yeah, but you'll eventually pass through.
No, because there's always some space
Oh,
left.
so it's always just gonna keep moving.
So you always get closer and closer, but you never get there.
You could be like,
Figure it out mathematically. If you do, so here's, if you think about it mathematically, Matthew, you start at 100. Say I'm 100 meters away from the wall.
So it's 50,
Time to be 50, then what?
25,
25,
and like 12.5. Yeah, 12.5.
12 and a half, 6.25. Okay, if you continue, even if you try and do the math, divide by 2 every time, it's never going to equal 0.
Yeah, but you're gonna.
Try it on your calculator. I mean, you'll be here forever, literally. Trying to get to 0. Okay, let's talk about this. Will be our last topic: heat and temperature, because they are two different measurements or two different things, although they are related. So, temperature is a measurement of the average movement of the molecules. Okay. Whereas heat is a measure of the total energy within the system. So heat depends on two things: how many molecules there are, and also how quickly those molecules are moving.
Is that when you put a solvent in, you're adding more molecules?
As far as boiling point and stuff?
Yeah.
No, not quite. So, also the type of molecules is related to the amount of heat. So if I try to explain in terms of an example, if I have, let me write on the board for a second. Let's say, this morning my driveway is super icy, probably like yours was. Was your driveway icy this morning? Yeah. All right, so if I want to try to melt that ice, I'm going to pour some hot water on the sidewalk in front of my house so nobody falls. All right, so let's say I have some water. Let's say I have a gallon of water. And I have some water that is 99 degrees Celsius, and I have some water that's 60 degrees. But no, let's say 80 degrees. Which one should I use to melt the ice in my driveway?
It's 60 to 80 degrees.
Why 80?
Because it will cool slow.
David?
You get a lot of steam.
No, I won't get steam from either one. So neither one are above boiling. Sir?
If it goes too fast, so like it won't work as well.
No.
99 Celsius.
Which one has a higher temperature? Which one has more heat? Right. This would be the better one to use. Now let's say I change this, and I have 100 gallons of 80 degrees Celsius and 99 degrees, and 1 gallon of 99 degree water. Should I still use the one with a higher temperature?
No.
What do you think? Who wants to give me your logic? Yeah, Matthew, what do you think?
Yes, because the amount really doesn't matter. It won't change anything.
Okay. Yusuf?
If every 1 gallon of that is 99, every 1 gallon of that is 80 degrees, 2 gallons of that would equal 1 gallon of that, or more.
Okay. Kimberly?
Because there's more, I think I'd say, I don't know which one, but it has to do something with the number of molecules.
It does. Which has a higher temperature? One. Which has a greater amount of total heat? Two definitely does. And the more heat, the better it would melt that ice. So here's the difference. Temperature is a measurement of the average movement of the molecules, whereas heat energy is a measure of the total amount of energy in there. So this would have greater heat. This one has higher temperature, but this one has more heat. It's like if you had to stick your finger in a tiny little thimbleful of boiling water,
Is it an actual thimble?
or a giant pot of boiling water.
Is it an actual
Which would you rather stick your finger in?
Is that an actual thimble?
Yep.
Is it a thimble?
The thimble.
Is it actually a thimble?
If somebody's going to pour this on your hand, boiling water,
Thimble.
which one would you rather have somebody pour on your arm?
I would rather take the big bucket.
Okay, let's say this. This is boiling water. This is not boiling,
The bucket.
but pretty close. Which would you rather have poured on your arm? Still the thimble. This has a higher temperature, but less
They would drop the thimble
total
and
heat.
sear me.
This one has a lower temperature, but a much greater total heat.
Thimble wouldn't have water in it because the thimble has holes in it.
They would keep pouring in water until it